Welcome to this rigorous scientific lecture on atomic force microscopy. Today we'll explore how AFM converts nanometer-scale cantilever deflections into quantitative measurements of surface forces. This is a fundamental technique in nanoscience that allows us to measure forces at the Piconewton-Scale. The central question we need to answer is, how do we go from a measured deflection of a flexible cantilever to an actual force value in newtons? And how do we ensure our measurements are accurate and reproducible? We'll follow a systematic 5-step workflow that any experimentalist would use. Step 1. Cantilever calibration. Step 2. Acquiring force distance curves. Step 3. Separating long-range from short-range forces. Step 4. Fitting contact mechanics models. Step 5. Validation using materials with known properties. Let's begin with Step 1. Cantilever calibration. This is absolutely critical because all subsequent measurements depend on knowing your cantilever spring constant accurately. Here's a schematic of an AFM cantilever. It's essentially a microscopic diving board, typically 100 to 200 micrometers long, with a sharp tip at the end. When forces act on the tip, the cantilever deflects. The cantilever obeys Hooke's law. Just like a macroscopic spring, the force equals the spring constant times the deflection. F equals K times delta, where F is force in newtons, K is the spring constant in newtons per meter, and delta is deflection in meters. Typical AFM cantilevers have spring constants ranging from 0.01 newtons per meter for soft biological samples up to 100 newtons per meter for hard materials like ceramics. You might ask, why not just use the same cantilever for all experiments? The answer relates to sensitivity and force range. Soft cantilevers with low K values give you high deflection sensitivity. A small force produces a large, easily measured deflection, but they have a limited force range before they bottom out. Stiff cantilevers can handle large forces without excessive deflection, but they're less sensitive to small forces. You need to match your cantilever to your sample. The most accurate calibration method is thermal noise analysis. This uses the equipartition theorem from statistical mechanics. 1/2 kBt equals 1/2 K times the mean square deflection. Here Kb is Boltzmann's constant, T is absolute temperature, K is the spring constant, and delta squared in brackets is the mean square thermal deflection. Even when nothing is touching the cantilever, it's constantly jiggling due to thermal energy from the surrounding molecules. By measuring this thermal noise, we can determine K. Rearranging, K equals kBt divided by the mean square deflection. This is beautiful because it requires no external calibration standards. Let's do a quick back-of-the-envelope calculation. Suppose we measure a root mean square thermal deflection of 0.5 nanometers at room temperature. Room temperature is 298 Kelvin. Boltzmann's constant is 1.38 times 10 to the negative 23 joules per Kelvin. The mean square deflection is 0.5 nanometers squared, which equals 2.5 times 10 to the negative 19 square meters. Therefore, K equals 1.38 times 10 to the negative 23 times 298 divided by 2.5 times 10 to the negative 19. This gives us approximately 0.016 newtons per meter. This is a typical value for a soft cantilever. Now that we have calibrated our cantilever, we move to Step 2, acquiring force distance curves. This is the core measurement in AFM force spectroscopy. We use a piezoelectric actuator to move either the sample or the cantilever base in a controlled manner. As the tip approaches the surface, we record the cantilever deflection as a function of piezo displacement. Here's the setup. The sample sits on a piezo stage that can move with sub-nanometer precision. As the piezo extends, bringing the sample closer to the tip, the cantilever deflects. A laser reflects off the back of the cantilever onto a position-sensitive photodetector to measure this deflection. A typical force distance curve has several distinct regions that tell us about different interaction regimes. Let me draw a typical force distance curve. The horizontal axis is distance or separation between tip and sample. The vertical axis is force, with positive values being repulsive and negative being attractive. Region 1. When the tip is far from the surface, there's essentially zero force. The curve is flat along the baseline. Region 2. As we approach, we start seeing long-range attractive forces. These are typically van der Waals forces, which scale as 1 over distance to the 6th power for molecule interactions, or 1 over distance squared for macroscopic bodies using Hamaker theory. Region 3. If the force gradient exceeds the cantilever spring constant, we get a mechanical instability called jump to contact. The tip suddenly snaps onto the surface. This happens when the derivative of force with respect to distance exceeds k. Mathematically, dF dz greater than k leads to instability. This is a critical concept in AFM. Region 4. Once in contact, the force becomes strongly repulsive. This is due to Pauli exclusion preventing electron cloud overlap. The curve becomes very steep, and the slope in this region tells us about mechanical properties. The photodetector gives us a voltage signal that's proportional to deflection. We need to convert this to actual force values. The conversion chain is voltage to deflection in nanometers, then deflection to force in nanonewtons using our calibrated spring constant. We calibrate the deflection sensitivity by pushing the cantilever against an infinitely hard surface, like sapphire. In this region, every nanometer the piezo moves equals exactly 1 nanometer of cantilever deflection. This gives us the voltage to nanometer conversion factor. Step 3 is crucial for quantitative analysis. We must separate long-range forces from short-range contact forces. These have completely different physical origins and distance dependencies. Long-range forces are dominated by van der Waals interactions. For an AFM tip, which we can model as a sphere near a flat surface, the van der Waals force is given by the Hamaker equation. F van der Waals equals negative HR over 6d squared, where h is the Hamaker constant in joules, r is the tip radius in meters, and d is the separation distance in meters. The negative sign indicates attraction. Typical Hamaker constants are around 10 to the negative 19 joules for materials in air. Tip radii are typically 10 to 50 nanometers for sharp tips. An important question: how far out do van der Waals forces extend? Let's estimate. Using h equals 10 to the negative 19 joules and r equals 20 nanometers, at a separation of 10 nanometers, we get a force of about 10 piconewtons. This is detectable with a sensitive cantilever. At 100 nanometers separation, the force drops to 0.1 piconewtons, which is at the noise floor for most instruments. So van der Waals forces effectively extend out to about 100 nanometers. In addition to van der Waals, we often have electrostatic forces if the tip and sample have different work functions or surface charges. These scale as 1 over distance squared for a charged sphere near a plane. The strategy is to fit the long-range portion of the curve, far from contact, to an appropriate model combining van der Waals and electrostatic contributions. Then we subtract this fitted long-range force to isolate the contact mechanics. Step 4. Once we've isolated the contact region, we fit it to a contact mechanics model to extract quantitative mechanical properties like elastic modulus and adhesion. The foundation is the Hertz model, developed by Heinrich Hertz in 1882 for elastic contact between curved surfaces. F equals 4/3 E star times the square root of R times delta to the 3/2 power. Here F is the load force, E star is the reduced modulus, R is the tip radius, and delta is the indentation depth. The 3/2 power law is characteristic of Hertzian contact. This nonlinear relationship between force and indentation arises from the geometry of contact between curved surfaces. The reduced modulus E star equals E over 1 minus nu squared, where E is Young's modulus and nu is Poisson's ratio. This accounts for the fact that both tip and sample can deform. If the tip is much stiffer than the sample, which is often the case with silicon tips on soft polymers or cells, then E star is essentially just the sample's reduced modulus. The Hertz model ignores adhesion. The Derjaguin-Muller-Toporov, or DMT model, extends Hertz by adding a constant adhesive force. F equals 4/3 E star square root R delta to the 3/2 minus F adhesion. The adhesion force FAD is related to the work of adhesion, and tip radius by FAD equals 2 pi r times work of adhesion. For materials with strong adhesion and low modulus, like rubber, the Johnson-Kendall-Roberts or JKR model is more appropriate. It treats adhesion as acting inside the contact area. The JKR equation is more complex. F equals 4/3 E star square root R delta to the 3/2 minus the square root of 8 pi E star R gamma delta cubed, where gamma is the work of adhesion. Choosing between DMT and JKR depends on the dimensionless Tabor parameter, which compares adhesive forces to elastic restoring forces. For hard materials with weak adhesion, use DMT. For soft materials with strong adhesion, use JKR. In practice, here's how we fit the data. First, identify the contact point where the tip touches the surface. This is where the force curve transitions from long-range attraction to steep repulsion. Second, convert the piezo displacement Z into actual indentation depth delta. The relationship is delta equals Z minus Z, contact minus deflection of the cantilever. This is critical because the cantilever itself bends. Delta equals Z minus C0 minus D, where Z is piezo position, Z0 is the contact point position, and D is cantilever deflection. Third, plot force versus indentation and fit to your chosen contact mechanics model. Use nonlinear least squares regression to extract E star and adhesion parameters. Let's work through a concrete example. Suppose we measure polystyrene, which has a known elastic modulus of about 3 gigapascals. We use a silicon tip with 20 nanometer radius and a cantilever with spring constant 0.5 newtons per meter. Using the Hertz model, let's predict the indentation at 10 nanonewtons load. Inverting the Hertz equation, delta equals the quantity 3F over 4 E star square root R, raised to the 2/3 power. For polystyrene with Poisson ratio 0.33, E star equals 3 times 10 to the 9 pascals divided by 1 minus 0.33 squared, giving us 3.36 gigapascals. Plugging in F equals 10 nanonewtons, E star equals 3.36 gigapascals, R equals 20 nanometers, we get delta approximately 1.2 nanometers. This is a measurable indentation. Step 5, and this is absolutely essential, validation. We must test our entire measurement and analysis pipeline on materials with independently known mechanical properties. Use standard reference materials like fused silica with E equals 72 gigapascals or polystyrene films. Measure multiple locations, multiple tips, multiple samples. A rigorous validation is the round-robin test. Predict the force distance curve for a material using literature values of E and adhesion. Then measure it. Do they match? Let's discuss common sources of systematic error that can invalidate your measurements. Error 1. An incorrect spring constant scales all your forces. If you're off by a factor of 2 in K, all your forces are off by a factor of 2. This is why calibration is so critical. Error 2. Tip radius. The Hertz model depends on square root of R. If your tip is blunted from 20 to 50 nanometers, your extracted modulus will be wrong. Characterize your tips with electron microscopy. Error 3. Surface roughness and contamination. AFM assumes smooth surfaces. Roughness on the scale of the contact radius invalidates continuum contact mechanics. Clean your samples thoroughly. Error 4. Rate-dependent effects. The models we discussed assume elastic behavior, but polymers and cells are viscoelastic. If you indent too fast or too slow, you'll get different apparent moduli. Control your velocity. Once you've mastered single-point measurements, you can create force-volume maps. This means acquiring a complete force-distance curve at every pixel in an image. This generates a three-dimensional dataset, x and y position, plus the full force-distance curve at each point. You can then create maps of modulus, adhesion, or any other parameter. This is incredibly powerful for heterogeneous samples like biological cells, where you want to map stiffness variations across the membrane, or composite materials with different phases. Let's do one more quantitative example to appreciate the forces involved. What pressure are we applying during a typical indentation? Consider our previous polystyrene example. 10 nanonewtons force, 20 nanometer tip radius, 1 nanometer indentation. The contact radius A equals square root of R times delta, which is square root of 20 times 10 to the negative 9 times 1 times 10 to the negative 9, giving us 4.5 nanometers. The mean pressure P equals F over pi A squared, which is 10 times 10 to the negative 9 divided by pi times 4.5 times 10 to the negative 9 squared. This gives us 157 megapascals. This is an enormous pressure. comparable to the material's hardness. We're locally creating extremely high stresses in a nanoscale contact. This is why tip wear is a concern, and why plastic deformation can occur even at seemingly small loads. Speaking of tip wear, this is a major practical concern. Each indentation can potentially damage the tip, blunting it and increasing the effective radius. The strategy is to regularly check your tip by measuring a reference sample with known properties. If the extracted modulus starts to drift, your tip is likely changing. Replace it. Operate at the lowest force that still gives you good signal-to-noise ratio. There's a trade-off between large indentation for good signal versus minimal tip damage. Let me summarize the complete workflow we've covered today. Step 1. Calibrate your cantilever spring constant using thermal noise analysis. This is the foundation of all quantitative measurements. Step 2. Acquire force distance curves by approaching the tip to the surface while recording deflection. Aim for sub-nanometer resolution in both force and distance. Step 3. Identify and subtract long-range forces like van der Waals and electrostatic interactions. Fit the non-contact region to an appropriate model. Step 4. Fit the contact region to an appropriate contact mechanics model. Choose Hertz, DMT, or JKR based on your material system. Extract elastic modulus and adhesion. Step 5. Validate your entire pipeline by measuring materials with independently known properties. If you can't predict literature values, something is wrong with your calibration or analysis. Beyond the technical workflow, let's highlight the key physical insights from today's lecture. AFM can probe forces over 6 orders of magnitude, from 1 piconewton for weak molecular interactions up to 1 micronewton for contact mechanics. Contact mechanics is fundamentally nonlinear. The 3/2 power law means force increases faster than linearly with indentation due to the increasing contact area. At the nanoscale, adhesion and elasticity are intimately coupled. You cannot simply add them. The contact area itself depends on the adhesive forces through the JKR or DMT models. Finally, where is this technique used in real research? In biophysics, AFM force spectroscopy measures the stiffness of living cells, maps the mechanical properties of membrane proteins, and can even unfold single molecules to measure their energy landscapes. In materials science, it provides nanoscale mechanical property maps of composites, thin films, and nanostructured materials. You can correlate structure with mechanical function at unprecedented resolution. In polymer physics, AFM studies adhesion, friction, and viscoelastic properties of polymer surfaces and interfaces. This is critical for understanding adhesives, lubricants, and coatings. To close, atomic force microscopy transforms a conceptually simple measurement, the deflection of a cantilever, into quantitative nanoscale force measurements through rigorous calibration, careful modeling, and systematic validation. The key is understanding the physics at every step, from thermal fluctuations determining spring constants, to contact mechanics governing indentation, to careful separation of different force contributions. Master this workflow, and you have a powerful tool for probing the mechanical world at the nanoscale.